Welcome to EDU World Space.
We're asked to use Mohr's circle to show that for any regular polygon, the area moment with respect to every axis through the centroid is the same. And the area product with respect to every pair of rectangular axes through the centroid is 0. So this problem all comes down to symmetries, and the symmetries that all regular polygons will have. So as they suggest in the book, we'll take a pentagon, for example. But again, this could be, we could do this for any regular polygon. So we have about this x and y axes. Okay, so this doesn't go through there, but we know we have symmetry about this y-axis, and we can always orient like a hexagon or a hexagon or whatever we have with respect to one axis, and we're going to have symmetry. And so that symmetry says that the area product about these axes is 0, so that these are principal axes, which then says that either Ix or Iy is the maximum. And we can just say, let's say Ix is the maximum. Okay, there's no loss in generality by assuming this, because we could just look at the other case and it would everything would follow. And so what we can do is say that, okay, let's rotate this axis, okay, and rotate it such that we have the new axes passing through the center of one of these sides of the polygon. And I've kind of drawn this one bad. This should not go through that center of that guy, just because of the geometry. This should go through something like that. All right, so there's y prime. And now that's not at the center of this, but x is at the center of this guy. And now we see we have symmetry about that axis. And so about that axis, about this set of axes, I, x, y, should be again 0. But we rotated by some angle here that was not 90 degrees, right? Or less than 90 degrees. If we'd rotated 90 degrees, we'd expect again to get back to here. So if we were here and we rotated 90 degrees, we'd expect to get back to here, and then I, x, y would be again 0. But we rotated something less than 90 degrees. So, and whatever it is for a pentagon, alpha, or whatever it is for whatever regular polygon we have, it's going to be less to rotate to get to another axis of symmetry. It's going to be less than 90 degrees. So this will be less than 180 degrees. So we're going to be, say, up here and here. But that would say that I, x, y prime has to be non-zero. But we know that it's 0. And so the only way that that can be reconciled is if r is 0. So that means that I, x bar and I, y bar have to be equal. And we saw that for a square, obviously. It's not so clear for other polygons, but that's true. So again, these are about the centroid anyway, equal. So we have that's true, and so then we know that this has to be also true, that it has to be, they have to be both the same, so that has to be the center. And so no matter how we rotate about this point, we're still at that point. So I, x prime, y prime is going to be the same, have the same values. So no matter, because for any regular polygon, it's r, the radius of Mohr's circle is 0. So Mohr's circle collapses to a point. And so we have the area moments about any axes are going to be the same. Rotated, any centroidal axes are going to be the same. And likewise, that just says that the area product about any centroidal axes is going to be 0. So that means that basically, if we have a regular polygon, then bending it about any axis is going to be just as strong. It doesn't matter what axis. It'd be just like we had a circle. And in fact, what we can say is that any regular polygon it can be thought of as just a circular cross section, okay, with the appropriate radius, because no matter which axis we bend around, try to bend this thing, it's going to have the same stiffness properties, just like a circular cross section would. And it's all because of symmetry. Okay, so there are certain symmetries that appear in Mohr's circle, and they don't agree with these symmetries here. So then we have to have some constraints, and that constraint says that that the principal area moment, all axes that pass through the centroid are principal axes.